So yeah, today I'm going to be talking about privacy. Is it working? Oh.
Say again?
Now? Is it good? Yeah.
No, it's good.
Okay, cool, thanks. All right, so privacy preserving smart contracts using fully homomorphic encryption. So just a brief intro, Zama is a cryptography company which provides open source homomorphic encryption solutions for both blockchain and artificial intelligence. So the agenda for today is going to be a quick intro to FHE, and then we're going to talk about what that means in the context of blockchain. I'm going to skim the surface of how the FHE VM works, and then I'm going to discuss challenges and research avenues for you students in here. All right, so fully homomorphic encryption, or FHE, is a type of encryption that allows computation to be done over encrypted data. So in this classical scenario where a user wants to offload computation over sensitive data to a server, it can encrypt its data X with its secret key that it generated, send over the encryption of X together with the public key to a server, which can then evaluate any function F over the encryption of X. And the result will be the encryption of the function F evaluated at X. And so this is where the homomorphism comes into play. Afterwards, the server or the cloud, whatever, can send back the encrypted response to the client, which can decrypt it and observe the function evaluation on the plain text data. And with more recent FHE schemes, you can do all sorts of function evaluation. So any univariate function you can evaluate on the ciphertext. You don't have to go through arithmetic circuits and encode any computation in addition and multiplication gates. You can do less than or equal, you can do sine, cosine, all sorts of stuff. And so if you have heard about FHE, maybe you've heard that FHE is still too slow to be used in practice. And while this is true in certain cases, we feel that in the blockchain case where users are already pretty used to very slow systems, the FHE overhead isn't that bad, right? So with our current system, we're able to reach around 5 ERC20 equivalent transfers per second. And we estimate that with the coming of custom hardware for FHE computation, we're going to be able to reach more than 1,000 TPS for a fraction of the cost. And also, go to mass adoption of FHE. All right, so now let's discuss what FHE means in the context of blockchain. As you all know, blockchain data is public by default. I don't think that's a feature. I think it's a necessity for the consensus protocols to work correctly. And so this can lead to several issues. First of all, you can be targeted for theft. There's actually a guy in my hometown who got kidnapped last week and had to pay like $25,000 of crypto before getting found by the police. So this is a real threat. You know, some people, if their balance of tokens is known to the public, they might be victim of theft. You can also be surveilled by your government, which might not be ideal, depending on where you live. And also, this isn't really a privacy issue, but the fact that everything is public on the blockchain leads to MEV concerns, where all users have to sort of pay this hidden tax on every transaction. And so now let's discuss what we can do now that we have FHE and this privacy issue in blockchain. So we thought of doing what we call the FHE VM, which integrates FHE into blockchain. You'll notice the naming convention is sort of borrowed from the ZK EVMs. If you're familiar with ZK EVMs, in our case, we don't actually prove the whole state transitions in FHE. What we do is we augment the EVM's feature set in order for contracts to be able to compute over encrypted data. So what we get out of this is end-to-end encryption of transaction data, or some transaction data and some state. We maintain composability and data availability on-chain. And we also don't break any DApps that are existing currently on EVM-based networks, right? Since we only augment the feature set, anything that runs on any EVM-based network right now can also work on the FHE VM. And we managed to do so without putting any compromise on transparency and usability. So since the FHE computation is deterministic, it is still publicly verifiable, right? The validators proceed to reach consensus using any consensus mechanism as usual, and external users can still verify that this happened correctly on-chain by redoing the computation locally. We also address one of the issues that was mentioned in the previous talk, where some data needs to be viewable by some parties, other data can be viewable by any parties, and this is what we call programmable privacy. And in that idea, like smart contracts can really enforce rules on which party can view which data, and a party can be an externally owned account or another smart contract using code, Solidity code. And we also maintain the composability paradigm, which is quite present in the EVM-based systems. So smart contracts who own ciphertext can call out to other smart contracts for computation to happen on their ciphertext and get results from that. And as you can imagine, this unlocks a ton of new use cases. You can think of tokenization of private real-world assets, fully blind auctions, completely on-chain, with several bids coming from several different parties. You've got games. Actually, in games, that's very interesting because you can generate encrypted bits using FHE and oblivious pseudo-random functions. So you can actually generate randomness directly on-chain without having to rely on the random oracles, blockchain random oracles. You can also get confidential voting, encrypted DIDs, and of course, private transfers. So now, let's skim the surface of how the FHE VM works. In the following slides, the gray dots are going to denote validators, and yellow dots are going to denote what we're going to call KMS, or Key Management System, or also MPC, which stands for Multi-Party Computation. And I'm also going to call those threshold nodes. And these are three names for the same thing, essentially. So we have this blockchain network that's being operated by validators, and the key management system that's being operated by some semi-trusted set of parties. Right? This isn't permissionless. This can be. On the left, you got the proof-of-stake consensus running. On the right, there's no such thing. Yeah, the box on the left holds the public key, the global public key to the system, and the box on the right holds the secret key for the system. And it's also shared between every node, such that no single node knows the entire secret key. And so how that works is that at the genesis of a blockchain system, the blockchain can ask this KMS, the key management system, to do a threshold key generation. And so the MPC nodes start out with nothing apart from knowledge of each other, and end up with a share of the secret key as well as a public key. And all the while, no KMS node has ever learned the complete secret key. The public key is made available for download to the public. When a user wants to send encrypted data as part of a transaction to the blockchain, they can use this public key, encrypt their data, and send over what we call the certified ciphertext, which is essentially the encryption of X with another cryptographic component that I'm going to mention later on. Whenever you have smart contract execution that needs to compute over encrypted data, the validators simply execute the smart contracts as usual. You know, the smart contracts own the ciphertext. The validators operate on the ciphertext using FHE operations and reach consensus on the results. Now, that's the interesting bit. I forgot to mention before, but the two boxes, the blockchain and the KMS, you can assume for today that they communicate with each other with some sort of bridge. Okay, we're not going to go into the details of that because that's a bit complicated. But yeah, let's just suppose there's a bridge in between the two. Now, suppose a smart contract owns a ciphertext, say E of X, and wants this value to be made available for the public to see. For example, maybe there was a blind auction, and the smart contract decides that the blind auction has ended, and it wants to publish the winner as well as maybe all the bids. It has to query the key management system in the fashion of how smart contracts query Oracle networks, and ask for the decryption of the ciphertext. Now the threshold network can proceed in this MPC protocol and produce the plain text X, which is then returned back to the blockchain. Now, suppose that a user which is entitled to see some value in a smart contract, for example, its encrypted ERC20 token balance, wants to view it. What it does is it generates a key pair, the public key of which we're going to call PK prime, and sends that together with the ciphertext, E of X, to the KMS network. It has to send that also with auxiliary information that convinces the MPC network that this very user is allowed to decrypt this very ciphertext. Now, the threshold protocol takes pk prime and E of x and engage in a threshold re-encryption protocol in which they produce E prime of x, which is x encrypted under the public key pk prime, all the while never learning the value x itself. So x is kept secret from the blockchain network, from the MPC network, and also it's in transit, coming back to the user, it's secret, and only the user who generated pk prime, which is just a classical libsodium public key. And only this user can decrypt the re-encrypted ciphertext. Now, I glossed over many details in that whole system, but maybe I can give you a couple more. So the way we manage to have smart contracts execute FHE operations, which are too heavy to be executed using EVM bytecode, is we introduce a few more precompiled smart contracts, which basically escape the EVM execution environment in order to call out to our custom-made Rust library implementing FHE operations. And also we have this notion of a certified ciphertext. This is when a user wants to send a transaction with encrypted data. This is the further cryptographic component I was referring to. Basically, they have to produce a zero-knowledge proof of knowledge that this ciphertext was correctly formed and that they know the corresponding plaintext X. This basically prevents malicious users from copy-pasting ciphertext from the blockchain state and simply sending it over to a malicious smart contract. And we keep track basically of those ciphertexts, right? So they come into the blockchain system as honestly encrypted ciphertext, and over time they maintain like this honestly obtained status. So maybe let's look a bit at how this can look, how a smart contract on the FHE VM can look. So here I have a very dumbed down example of the encrypted ERC20. And notice that at the top we have the balances, which is a state variable, which is a mapping from addresses to encrypted unsigned integers. Now in the transfer function, which receives two addresses as usual, and an encrypted unsigned integer as the amount to transfer, we can't do branching statements using if statements or require as usual because all the data here is encrypted, right? So what we're going to do is compute an encrypted Boolean that encodes whether or not the sender has enough funds to perform the transfer. Then we can multiply this encryption of 0 or 1 with the amount that was sent as argument, and then proceed to do the addition and subtraction over the balances. Notice that these two last operations, they're going to be no ops if the sender didn't have enough funds. So we're just going to add 0 and subtract 0, or encryptions of 0. And all validators and all the public is oblivious to the actual amount that is being transferred. All right, so maybe now for the more interesting part for researchers out here is what kind of challenges and what kind of challenges we encountered while building this, and what are the next research avenues. So first of all, the big thing, scaling. As I said, we get around 5 TPS. How do we scale that? In the context of blockchain, usually scaling comes through rollups. But in this case, it's not clear how to create rollups from the FHE VM. If we take a look at the optimistic approach, where state transition is executed in some kind of VM, and then there's a dispute resolution maybe happening on the layer 1, this doesn't really fit the FHE paradigm because FHE operations are too computationally costly to be executed efficiently in VMs. We really make good use of this native execution environment that I was referring to earlier. And so we can't really think for the moment of executing FHE in WASM. But this is an open research topic. It would be a good project, I think. Now, if we take a look at validity rollups, aka ZK rollups, then again, it's not clear if we can generate snarks for FHE operations. Some recent work that I link in the bottom left try to tackle this issue. I think it's a very, very interesting subject because not only would it allow for scaling of the FHE VM, but also slapping snarks on FHE gives some stronger security guarantees for FHE schemes because FHE by definition is malleable, and so you can't reach some very strong security guarantees such as indistinguishability against chosen ciphertext attacks. But when you use snarks over FHE, you can get some stronger security guarantees. You could also consider hybrid rollups, right? So if we know that snarks for FHE are very long to generate, you can maybe consider the fact that, okay, we don't need to generate a snark for every batch of transaction. We can batch transactions, execute these batches optimistically until there's a whistleblower that says, oh, there's an error there. And only then do you have to generate a snark, which, I don't know, may take like a week to generate or something. So hybrid rollups may be a good trade-off in this case. Now, there's a big issue of incentives, because you may have noticed that the network on the right, the threshold network, every node in that network holds a share of the secret key, and nothing really prevents them from taking that share, meeting in some kind of back alley, and doing arbitrary decryptions. So there's a big question on whether or not we can incentivize MPC parties not to collude. There exists some theoretical work on the self-incriminating proofs of decryption, but as far as I know, that hasn't been implemented yet, and it's still only theoretical. There's also the question to study whether or not, or to what extent can trusted execution environments be used to prevent collusion in this case. And lastly, there's the big question of MEV, right? I don't think MEV in the context of private blockchains has been studied in depth. And there is this question about, like, can we prevent sandwiching and front-running attacks, all the while allowing for arbitrage opportunities to maintain efficient markets. And that concludes my talk. If you got inspiration for a cool project to build with FHE, please do visit our grant program. Zama will pay you to build cool stuff. Also, you can try this. We've got a white paper documentation. This is all live. We're hiring. And thanks for your time.
Yeah, thank you very much. Any questions? Oh, lots of questions.
Thank you very much for the great talk. I have a question regarding for the threshold encryption aspect. For how large do you actually consider the amount of peers be when it comes to having the individual shares? Did you do already some evaluations on that part? Because of course some of the threshold schemes do not scale as well when it comes to large number of peers themselves.
We've got ideas for what kind of protocols we want to run for the number of threshold parties equal to 4 and 10. And then we envision to switching to some kind of other protocol, which is maybe less efficient for a higher number of threshold nodes. But as I said, for the moment, we don't have a great idea on how to avoid collusion. So there might be some reliance on trust and reputation in this case.
Great, thank you.
So do you have any ideas how to grow the network? So let's say you start off with a 3 out of 3 threshold scheme, and then as you introduce more nodes into the blockchain, you would also want, I guess, the privacy guarantees to scale with the blockchain. Yeah. So how would you transition from then an N out of N secret sharing while still keeping the former records valid?
I'm no MPC guy. We have a ton of MPC experts at Zama, so maybe I'm not the right person to answer. But from what I know, we do have, so we have laid out some resharing protocols, which I didn't talk about here. So I'm pretty sure you can have like a threshold of MPC parties reshare the secret into a potentially different set of nodes.
I guess that would necessitate, though, to reshare the whole blockchain history to that new threshold sharing scheme.
So maybe not necessarily, right? So you can think that there could be an epoch in time where you need to like sort of re-encrypt every ciphertext on the chain under this new key. But what you could also do is generate a key switching key, which you can do in FHE, and sort of on the fly switch the ciphertext from the old key to the new key whenever they're used in smart contracts, which is very cheap to do.
Okay, thanks.
Yeah.
Peer-to-peer or more centralized control?
Okay, so very interesting talk. At the beginning you mentioned we could expect hardware acceleration to really accelerate fully homomorphic encryption. Yeah. Can you explain a bit when you expect that to see deployed, and which margins do we can we expect to get? And what is the energy, the whole solution?
I think this
with
is
cost?
the best way to answer. Yeah, we're working in close collaborations with KU Leuven, who has a accelerator program, in order to have FPGAs to compute entities, because this is the main bottleneck in FHE computation, is a number theoretic transform. And yeah, I guess I'm a research guy. I can't tell you more about the numbers. This is what we expect, 500 million gates per dollar.
Okay, thanks.
Yeah.
Another question? Yeah, I have a question about the type system, but we do this later offline of the language. Fine. Again, yes, a pressing question?
Yeah, just a quick question about the transactions per second.
Yeah.
So you have here million FHE gates per dollar. I was just wondering about million FHE gates per second that you can do realistically.
Oh, that's per dollar. I think it should say per second per dollar here. I think.
No. I mean, I'm not talking about this. I'm just interested in throughput of.
For the blockchain?
Yes.
We expect that if this number holds, this number is going to hold. So more than 1,000 TPS, or like ERC20 equivalent transfer per second in the blockchain case.
Do you know what's that equivalent in gates per second?
No.